Hey guys, today we're talking about using logarithms to solve exponential equations. Now, again, as we've been talking about this entire section, logarithms are exponents that you raise a base to in order to find the power. So if we're given a simple exponential equation like this, b to the x is equal to a, and we want to solve for that power, then we can rewrite this using logarithms. Logarithms will help us solve and find that exponent. So let's jump into a few examples and see exactly how we can use logarithms to solve these exponential equations. Here's our first example. It says solve 3 to the x is equal to 57. So I don't know what power I raise 3 to in order to get 57. 57 is not a perfect cube, so it's not going to be a whole number here. But what I do is I'm going to rewrite this as log of both sides. Now, what you do to one side of the equal sign, you have to do to the other side, which includes taking the log of both sides. Now, let's apply our power theorem of logarithms that says if we're going to take a log to some base to a power, we take that power and we put it down in front. So it becomes x times log 3 is equal to log 57. Now, I'm going to divide both sides by log 3. And when I divide both sides by log 3, I get x by itself. So x is equal to log 57 divided by log 3. Now, this is just simple operations on your graphing calculator. Go ahead to your graphing calculator, punch in log 57, divide by log 3, and you should end up with 3.68. Now, you can test that by going back to your original equation, take 3, raise it to the 3.68, and you should get pretty close to 57. All right, our next example is just like the previous. 5 to what power gives me 32? Now, we're going to take the log of both sides. So I'm going to rewrite my first line as log of 5 to the x power equals log 32. I apply my power theorem of logs that says take that power, put it down in front, and we rewrite that as x times log 5 is equal to log 32. And then we're going to divide both sides by log 5. That will get rid of it on this side. Now x will be equal to log 32 divided by log 5. And again, that will give us on our calculators 2.153. Don't take my word for it. Check it on your graphing calculator. Make sure you're getting it as well. All right, let's move into a little story problem here. It says recall the formula for interest compounding continuously is this PERT formula, right? The amount you have is equal to the principal times e to the r times t. At what rate of interest, so we're looking for r here, compounded continuously, do you have to invest your money so that it will triple in 20 years? So 20 is my value for t. We'll notice that we're not given an amount of money, but we do want it to triple. So it's okay to just start with the generic $3 will be tripling $1. So $1 is your initial investment. $3 is what you want it to go to. In other words, that's what would be tripling, right? E to the rate times 20. Okay, so you see here that our variable is in the exponent, and we want to solve for that. So instead of taking the log of both sides, we're actually going to take the natural log of both sides. So we'll take the ln of 3 is equal to the ln of e to the r times 20. Again, applying our power theorem of logarithms, that power comes down in front here. So I'm going to write that as 20r times ln of e. Now, the natural log of e is simply 1. So this is equal to just 20r. And to get r by itself, I'm going to divide by 20. So the natural log of e divided by 20 on our calculators, and again, check this, don't just take my word for it, should come out to equal 0.0549. So this is our rate. Now if we're going to write that as a percentage, that would be written as 5.49%. All right, example 3 says a math teacher has $60,000. Oh, that's all. Oh my goodness. Who's writing this material? This is so funny. All right, let's see. A rocket scientist has $60,000 saved for retirement. If he earns an average of 9%, oh yeah, see, this is a make-believe world, interest annually and makes no additional deposits or withdrawals, how long will he have to keep working to retire a millionaire? Well, I'm just going to go ahead and use real life experience and tell you forever on this one. All right, anyways, let's say $1 million is the goal. We'll solve the problem. I know you're curious now, right? $1 million is the goal. He's got 60 G's to invest. It's going to be compounded, an average of 9%. So let's write that as 1.09. It's going to be calculated annually. So I'm just going to leave it like this. It's not going to be divided by any number. And then how long, so that's t here, is my power that I'm looking for. So just like in the previous problem, we're going to divide both sides by 60, what is that, another 0, 60,000. Whoops. I'll get my commas correct here in a second. There we go, and there we go. All right, and there we go. Okay. And then that leaves us with 1.09 to the t power is equal to, that's going to cross off 1, 2, 3, 4. There's my 4 there. 100 over 6. So again, on your calculators here, I'm just going to do the math. That gives me 16.6 repeating is equal to 1.09 t. And now we want to take the natural, or sorry, not the natural log. We're going to actually take the common log of both sides. So we'll take log of this side. We'll take log of the other side. And we'll use our property of powers here. So this is t times log of 1.09 is equal to log 16.6 repeating. Now to get t by itself, we got to divide both sides by log 1.09. So we'll divide that by log 1.09. T, the number of years this poor teacher is going to have to keep working and influencing the lives of youngsters like you, is 32.6 years. But you know what? You guys make it seem so easy. I'll come back and do it. All right, let's skip example 4 because I like you guys so much. Let's move on to the last part here. This change of base theorem. For all positive real numbers a and b and t, where b is not equal to 1 and t is not equal to 1, then this change of base theorem kind of goes like this. Log base t, blanked out. Log base t of I got this. Goes like this. Log base b of a is equal to the natural log of a divided by the natural log of b. Okay, so real simple, easy to apply this thing. It says approximate log base 4 of 24. We're simply going to use this change of base theorem because there's 4 is not a perfect square or cube to get me 24. So I'm just going to rewrite this as log 24 divided by log 4, and that doing that on my calculator is going to give me my answer of 2.29. Now you guys got some fancy schmancy calculators. You can just type in log base 4 of 24 and get the same result. All right, one final example for today and for this section here. We got 1.5 equals e to the 0.08t. We're going to take the natural log of both sides, natural log of e to the 0.08t. We're going to take that and apply our power theorem again. So that gives me 0.08t times the natural log of e, which is just 1, is equal to the natural log of 1.5. So in the end here, this 1, I don't really even need to write it. I'm going to divide both sides by 0.08 to get t by itself. So t is equal to the natural log of 1.5 divided by 0.08, and that's going to give me 5.068. And that's a wrap for Chapter 9.